Hello everyone, and welcome back to this series on elementary statistics and probability. In this video we're going to be primarily focusing on different counting methods that are often used in different probability problems. We're going to begin by discussing the fundamental counting principle, which you most likely have encountered in the past, and then describe the three primary counting strategies that are often used, known as permutations, combinations, and derangements. As usual, we're going to give a few examples at the end of the video, just to make sure you can distinguish when to use each of them. Let's get started. Alright, so let's begin by stating what the fundamental counting principle says, and sometimes it's called FCP for short. So let us assume you have n1 distinct instances of object 1 and n2 distinct instances of object 2, and create a collection C of x1 and x2. Then there will be n1 times n2 different collections of these different objects. Of course, you can go from n1, n2, n3, n4 down to say nk, and have collections of these k objects if you want to, but this is the basic statement of the fundamental counting principle. So let's sort of get an idea of exactly what this FCP actually says with an example. So let us assume you go to a car dealership, and there's different kinds of cars, right? So the colors, for example, are, for example, red, green, blue, and black, and maybe white. So 5 different colors. And you can also get the type of car. For example, you can get a car, a truck, an SUV, or something like that. So if you can get a car, a truck, an SUV in any of these colors, how many different pairings could you possibly have? So the number of different types of cars that we're going to be looking at here is going to be equal to the number of colors that you could have, multiply the number by the number of types you can have, and that can give you the number of vehicles that you can come away with. So that's going to be, of course, 5 times 3 by the fundamental counting principle. Therefore, you're going to have 15 different vehicles that you could walk away with. So that's the fundamental counting principle, very basic. And keep in mind these objects here, R, G, B, BK, and W, car, truck, SUV, they'll have to be distinguishable, else you won't be able to tell the difference, right? So you can't have red and count that as 2. You can only count that as 1. All right. So the first type of counting method, aside from the counting principle, that people usually work with is what we refer to as a permutation. So let us consider a very basic example. Let us consider the word zebra, Z-E-B-R-A, and let us consider the rearrangements of these letters. So if I do the rearrangements of these letters, for example, I could have the original, that is, I do not permute anything. I could also change these 2 letters. I could get E, Z, and keep everything else the same, B, R, A. I could also have E, Z, A, B, and R, and you could probably list several more. So my question to you is, how many different rearrangements of the letters of zebra are there? Okay, so there's 5 distinct letters, right? So there's 5 distinct letters. And this word here, distinct, that's going to be important, and I'm going to give an example of what if you have repetitions of letters or something like that. So we have 5 different letters that can be in 5 different positions. And what do I mean by position? So we have 5 positions here. We have position 1, position 2, right here, position 3, position 4, and finally position 5 there, right? So I have 5 different letters that could be in any of these 5 different positions. So how many different rearrangements of these letters are there? So how many letters can go in position 1? So that's of course going to be equal to 5, right? So when I put that first letter there, I'm going to have 1 less letter than I started with. So since I started with 5, then I'm only going to have 4 different letters that could go into this position. So that's going to be 4. And since I used another one, I have 2 less than I started with, so I'm only going to be left with 3, then left with 2. And since I've used 4 out of the original 5, that means I only have 1 value that could go here. So therefore, the number of distinguishable rearrangements by the fundamental counting principle would be 5 times 4 times 3 times 2 times 1, which is actually the same as 5 factorial in case you've encountered this notation before. So that's going to be 5 times 4 is 20, times 3 is 60, times 2 is 120. So 5 factorial is equal to 120. So that is the number of permutations of these letters that there are. All right, so notice I'm choosing 5 of these letters out of my original 5, right? So original number is equal to 5, and we're choosing a particular number. We're choosing 5 of them. I'm going to change this up a bit, so I'm going to just state what I'm going to do in a moment. So the original number, this is usually what we denote by n, so n is equal to 5, and the number we're choosing is usually denoted by r, right? So we're going to write instead NPR, so the number that we're choosing from and the number we choose, this is going to be equal to n factorial, right? At least if r is equal to n. So NPN is going to be equal to n factorial by our fundamental counting principle. Okay, so what if we actually don't choose all of them, for example? So let us assume we have n is equal to 5 and we choose 3 of them. So in this case, r is going to be equal to 3. Okay, so for example, we have Z, E, B, R, A as our original set of 5 letters, and we're only going to choose 3 of them. So I could have Z, E, B, I could have Z, R, A, and so on. So how many different rearrangements would there be? So for the first position here, so we have 3 positions to fill, right? So we have 5 letters to fill in the first. So the number is going to be equal to 5. So once we choose one, we're only going to have 4 left, so 4. Then we have chosen 2, so we're only going to be left with 3. And there's only 3 positions to fill, right? So by the fundamental counting principle, we just have 5 times 4 times 3, which is just going to be equal to 60. So therefore, we write that 5p3 is going to be equal to 60. Now, is there a quick formula that we can use for this? Definitely yes, right? So if we look at this particular example, so our particular number is going to be equal to 5 times 4 times 3. So we can also actually make this a factorial expression by multiplying top and bottom of this expression by 2 times 1, right? So the top expression is just going to be equal to 5 factorial, which is just going to be equal to the n factorial. So what's this factorial equal to? That's just 2 factorial. So what's the relation between 5, 3, and 2? Well, this number 2 is just the same as 5 minus 3 factorial. So from here, one can show that NPR is actually equal to n factorial over n minus r factorial. Okay, so notice here that the order matters for all these different arrangements, right? So when I say order matters, that means this ZE is not the same as EZ. So these words, I guess you could call them, ZE and EZ, are not the same, right? Therefore, the order matters, and if you change the order, it results in a different outcome. All right, so what happens when you actually have some repetition going on here, right? So let's include or give a very common word, statistics. STATISTICS, statistics, right? So notice here that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So I have 10 different rearrangements. And if we make each of these letters different, then we're going to have 10 factorial different permutations of the word, right? But of course, if I switch, for example, this T and this T, I get the same exact word, right? And if I switch this I and that I, we're going to get the same exact word. And we don't want to count those words twice, right? So, also we have some repetitions of S, right? So we have S, S, and S there. So if we switch any of those S's, we also get the same exact word as well, okay? So the number of S's we have here is 3. We also have 3 T's, right? So the number of T's we have here is 3. And in terms of I's, we have 2. Right? And all of the other letters only represent each other once, so we should be okay there, right? So we have 10 letters, 3 S's, 3 T's, and 2 I's. The rest are unique, right? So 3, 6, 7, 8 letters are non-unique, I guess you could call them. Okay, and A and C are the special ones. So if we treat all of them differently, then the number of permutations is going to be equal to 10 factorial, but we don't want to count the things that repeat. So how many different rearrangements of, for example, S are there? So we have three different S's. We have S1, S2, and S3. So we don't want to count, for example, S1, 2, 3, and S2, S1, S3. Those will correspond to the same exact word. So how many different rearrangements of the s's are there? Well, there's clearly only going to be 3 factorial of them. And what about the t's? So how many different rearrangements of the t's will there be? So that's also going to be 3 factorial. And the number of rearrangements of the i's is also going to be 2 factorial, and we divide because we want to cancel them out from the original amount. And you can work out this calculation to be equal to 50,400. So quite a few different amounts of permutations of those letters, right? So this, of course, would be a modification of the fundamental counting principle. And if you're not choosing all of them, then you can use this very compact formula for permutations as well. So a key word that we're using here is that order matters. So if we change the order, we get a different outcome. But the next problem that we're going to look at is when order does not matter, and how we don't sort of how we can get around not calculating those. So we'll look at that in the next example. All right, so now let us consider the case where order doesn't matter. So we already said that if order matters, then this would be a permutation. So if order does not matter, then we're going to call this a combination. Right? Now, of course, if order does not matter, this implies a combination. With respect to the English word with like combination locks, of course, this is counterintuitive because for a combination lock, a particular order does necessarily matter. For example, if you have 1, 2, 3 and the code is actually 3, 2, 1, then that won't work, right? So in terms of intuition with respect to the word combination and combination lock, don't get confused with that. But if order does not matter, then combination. So when I say order does not matter, that means the sequence of elements 1, 2, 3 is equal to the sequence of elements 3, 2, 1, and is equal to the sequence of elements 2, 3, 1, and so on. So it has the first 3 digits of the natural numbers, I guess you could call them. They represent the same exact event. Okay? So how can we sort of figure out a quick way to count these types of things? So let's begin with a particular example that some people may be familiar with. Let us assume we play a video game or a football game or a basketball game or something. And let's assume we play 5 games. And let's assume we usually are guaranteed to lose 3 of them. Or let's say 2 of them. 3 is too much. 2 of them. Okay, so this is the scenario that we want to sort of count. How many types of scenarios sort of are represented by this description, okay? So you could have, for example, when, lose, lose. So that would be an event. And when, lose, that would be an event. And we could have lose, lose, win. So we start off bad and we finish off winning all 3 of them. That would be an event. So with respect to this description, all these 3 events are equal. So when I say order doesn't matter, notice that the order definitely is different, but in this case, order doesn't matter because we're trying to count the number of events that are described by this scenario. All right, so how can we sort of count these types of things, right? So if we sort of focus on the losses here, so we have a total of 5 events, and we're choosing pretty much 2 of them. So we're focusing on the losses, right? So we want to count how many events sort of satisfy this particular criteria. So this is again what we call a combination, and we're going to denote it by NCR. And one can find, and I'm not going to go ahead and prove this, but it's really related to the idea of permutations. This is going to be equal to n factorial over r factorial with n minus r factorial also on the bottom. So if you relate this to, for example, permutations, this is going to be npr all divided by n r factorial on the bottom. R factorial on the bottom. Okay, so NCR is equal to NPR over R factorial. Okay, so what can we say? So clearly, NPR over R factorial is clearly less than NPR. So we clearly see that the number of combinations for events is always going to be less than or equal to the number of permutations of those events. So we can clearly see that that's going to be true. Okay. So if you have 5 permutations, for example, that means you must have strictly 5 or less number of combinations, depending on what you're sort of working with. Okay. So if we use this formula that I'm sort of giving you here, I'm not going to derive it, of course, as I said. Let's see what we get. So 5 choose 2, and some people will actually write this as 5, 2. So this is usually what we refer to as a binomial coefficient. And I'll sort of go into a little brief discussion of why we call it that. So this is going to be equal to 5 factorial over 2 factorial times 5 minus 2 factorial. So what's that going to be equal to? So that's going to be equal to 5 factorial over 2 factorial, and 5 minus 2 is 3 factorial. So a quick way to sort of simplify these is I'm going to multiply 5 down until I get to one of these two on the bottom. So I have 5 times 4, and 3 factorial is the largest, so I'm going to stop there. And if you notice, if you stop at the largest, you can just cancel them out, right? So we're just going to be left with 5 times 4 all over 2 times 1. And 2 goes into 4 twice, so this is going to be the same as 5 times 2, which is equal to 10. Right, so that's how many different rearrangements of wins and losses there can be, provided that you play 5 games and you lose 2 of them. Okay, so let's actually talk about another way you can actually calculate this without using this little formula, and discuss where this binomial coefficient thing actually comes from. So let us consider, for example, x plus y to the power of 0, where x and y are real numbers. Sometimes we write that as that. Right? So anything to the 0 power is equal to 1, provided that the base is non-zero. So let's assume that that is the case. And let's also do x plus y to the power first. So everything raised to the first power is just itself. So that's going to be equal to 1x plus 1y. And I'm going to write those ones there for a reason that has become clear soon. So if you do x plus y to the power of 2, and you distribute the x plus y times x plus y, you're going to get that this is going to be 1x squared plus 2xy plus 1y squared. If you do x plus y cubed, then you can quickly get x plus y cubed by multiplying x plus y times this answer that I just got for x plus y squared. You're going to get that that's going to be equal to 1x cubed plus 3x squared y plus 3xy squared plus 1y to the power of 3. And if we can continue this, x plus y to the power of 4, that's going to give us 1 to the power of x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the power of 4. So the pattern on the x's and the powers of y's is pretty obvious, right? So if we look at x to the fourth, so this is clearly a y to the 0. So we got 4x, 3x, 2x, 1x, and then 0x at the very end. For y's, we have 0, 1, 2, 3, 4. So we're decreasing our x's from 4 to 0 from the left and the right, and we're increasing our values of y's from the left and right, or vice versa from the left, right? So what is the pattern on these coefficients? That might not be so obvious. So these are what we call the binomial coefficients, and are connected to those combinations that we briefly discussed. So this corresponds to n, and to position here, so this is going to be r is equal to 0, r is equal to 1, r is equal to 2, r is equal to 3, and this is going to be r is equal to n, which is always the highest power. So if you quickly want to figure out what the coefficient of x cubed y would be, all you need to figure out is 4, 1. So 4, 1, which of course is equivalent to 4c1, which is 4 factorial over 1 factorial times 4 minus 1 factorial, which is going to be 4 factorial all over 3 factorial, which is the same as 4 times 3 factorial all over 3 factorial, and they cancel, just leaving us with 4, and that gives us that coefficient, right? So this is where the idea of binomial coefficients and combinations sort of come into play. And you can actually generate this little pattern of coefficients via what we call Pascal's triangle, right? So how can we generate this pattern of Pascal's triangle? So we have 1, 1, and 1, 2, 1. So quickly, how do we generate this? So we're going to have ones on the boundary of the triangle, always. And then for the interiors, we're going to be adding together the values that are vertically above and below it, right? So this, of course, is going to be n is equal to 0. This is going to be n is equal to 1, and this is going to be n is equal to 2. So let's generate the row for n is equal to 3 and n is equal to 4, and then you can compare what we got before, right? So we're going to have 1 and 1 there. So the next we're going to have 1 plus 2, which is 3. 2 plus 1, which is 3. So that's 1, 3, 3, 1. And let's do the row for n is equal to 4. All right, so we're going to have 1 and 1 on the boundary. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and we get our pattern 1, 4, 6, 4, 1. And if we want to continue this pattern, we're going to have 1, 5, 10, 10, 5, 1 for n is equal to 5, for example. So if somebody wants to ask you, what is 5 choose 3? So, right, so you're going to look in the row for n is equal to 5. So we have 0, 1, 2, 3. So this is actually going to be equal to 10. Also, if somebody asks you to expand, what is x plus y to the power of 5? You're going to say that that's going to be equal to x to the 5 plus 5x4y plus 10x3y squared plus 10x squared y cubed plus 5xy4 plus y to the power of 5 using those coefficients and the increasing and decreasing powers of x and y, right? So that's a very beautiful geometric connection between expansions of binomials, because we have two terms, x and y, and also how it relates to combinations. So those are the two common methods for counting, permutations and combinations. Now let us talk about another method of counting that is known as a derangement. Alright, so now let us consider a third type of counting method that is often used. And remember, combinations was a special form of permutations, and this is also going to be a special type of permutation as well. So let us assume we want to count the number of permutations, but we're going to actually add a little rule to the game. In particular, that the objects cannot be in their original position when you consider the rearrangement. For example, if you have A, B, and C, and you consider the permutation A, C, B, this would not classify under this particular rule because A is in its original position, and we don't want to count that. So these types of permutations that we're going to consider, where the objects cannot be in their original position, is what we are going to refer to as a derangement. A derangement, okay? So the number of derangements of these particular objects, right? So if we have n particular objects and we want to count the number of derangements, we're typically going to replace or denote that by n with a factorial sign before it. Some people will write this as dn, but n factorial with a factorial symbol on the before end is usually the most common notation, at least now. So let us look at an example to sort of see if we can count the number of derangements of a particular set of objects without actually looking at a particular formula for it, right? So let us consider the set of objects alpha, beta, gamma, and delta. So the first four Greek letters, right? And we want to count the number of derangements for this. So what's an easy way to count them? So remember, alpha cannot be in its original position. So in position 1, the only values that can be there are going to be beta, gamma, and delta, right? So we're going to have beta, gamma, and delta, right? So all of the derangements must have either beta, gamma, or delta in the first position. So let's figure out all the possible values for which the derangements are such that beta is in position 1. Okay, so alpha can be in position 2, so that's okay. Gamma cannot be in position 3, right? So if beta and alpha start off in positions 1 and 2 respectively, then the next position must be delta, and the next value must be gamma, okay? So let's see if we can figure out another beta derangement, right? So we already figured out that if alpha is in position 2, then delta gamma is the only possible values that can sort of follow that, okay? So delta can also be in position 2, that's perfectly fine. Keep in mind, gamma cannot be in position 3 because it originally was there. So alpha must be the value that is in position 3, forcing gamma to be in position 4. So again, if beta is in position 1, and who's the next person that hasn't been in position 2? That would be gamma, right? So beta gamma, right? So alpha can be in position 3, but that would force delta to be in position 4, which can't happen, right? So that means delta must be in position 3 and alpha must be in position 4. And you can do by process of elimination that this is all the possible derangements such that beta starts this process. Let's do the same for gamma, okay? So if gamma is in position 1, alpha can be in position 2, that's perfectly fine. Then we can have beta in position 3, that's okay, but that forces delta to be in position 4. That's not okay. So that means if alpha is in position 2, that forces delta and beta to be in those positions. Similarly, beta cannot be in position 2. So that means delta is another possibility for position 2. We can have alpha in position 3. That's okay. And position 4 for beta. That's okay too. We could also switch alpha and beta in that order as well. Why not? That's not a problem. So beta alpha, so that's okay. Let's look at the possible values of delta. So if we have delta here, we can have alpha in position 2. We can't have gamma in position 3. And then we can put beta in position 3 if we want to. So if we start off with alpha, we can't have beta in position 2. So we can, for example, have we can have gamma there. That's okay. We can have alpha here and beta there. And also we can permute those two as well. So beta and alpha. So we see that if n is equal to 4 by process of elimination, we only have 3, 6, 9 different derangements of these objects. That is, they cannot be in their original position, right? So we're going to write this instead for derangement. Some people also will say this is for subfactorial. Some people will say that. So 4 subfactorial is going to be equal to 9. Now, of course, if I make this number n a little bit large, this might take a little while, so being able to build a little formula for the subfactorial or the number of derangements is definitely beneficial. I'm not going to get into the derivation of this. There are several resources and PDFs and books that actually derive this. So I'm just going to actually add this just as a little theorem. And you can derive the proof if you want to or feeling adventurous, okay? So n subfactorial is actually equal to n factorial times the finite sum from k is equal to 0 to n of the alternating series -1 to the k all over k factorial. So how would you use this definition? For example, if you have 4 subfactorial, this is going to be equal to 4 factorial. We already know how to do that, 4 times 3 times 2 times 1. And then we're going to alternate the sum. So we're going to have -1 to the 0 over 0 factorial plus -1 to the first over 1 factorial plus -1 to the second over 2 factorial plus -1 to the third over 3 factorial plus -1 to the fourth over 4 factorial, right? So once you actually work all this out, you're actually going to get 9 in the end. So you can trust me on that or work that out on your own. Although this is a closed form expression, this can also be a little bit messy if you do this by hand, especially if I could say what is 50 subfactorial. Of course, these terms is a decreasing sequence aside from the alternating part, because as n grows big, factorial grows big, so this quotient grows smaller, right? So if you want to approximate, for example, you can grab the first n terms, I guess you could call it, and use that as an approximation since these terms are decreasing with respect to the alternating portion. Right? So there is another formula that actually most people use, and that is the following. So n subfactorial is going to be equal to the floor of n factorial divided by e plus 1/2. So this notation usually is denoted by floor, which pretty much means round down. So for example, if I say floor 1.2, that's of course going to be 1. And if I say 1.999 and floor that, that's also going to be equal to 1. So even though it's closer to 2 and we usually would round up, floor just means round down, right? And this number e here, everyone should know what that is. That's approximately equal to 2.71828 and so on. Most calculators have that number programmed in it, and it's the base of the natural logarithm, okay? So just as an example, if we want to calculate 4 subfactorial via this relationship, so this is going to be equal to the floor of 4 factorial all over e plus 1/2, and that's going to be equal to the floor of 9.321. It should be, yeah, 9 approximately. And of course, if we round that down, we're going to get our normal answer of 9. Okay, so those are our 3 prime, or actually 4 um, relationships that we usually use for counting. So we have our fundamental counting principle, then we have our permutations, then we have our combinations, and then we have our derangements. Of course, you can add some special rules to each of these and make your own special counting method, and if you're lucky, maybe even come up with a special rule on how to quickly calculate them if I give you a particular natural number n, or if you're selecting things, a particular natural number r. Anyway, if you enjoyed this video as always, please like and subscribe, and stay tuned for some exercises that you can measure your understanding in this video. Hope you enjoyed, and I'll see you in the next lecture. See you, everyone.